Hello, I'm happy to be able to give you a talk by this video conferencing. Of course, it would be nicer to be there, but it's impossible these days. So we all use now electronic means to go around the world without moving from our office. I listened to a little bit of the presentations which were before my talk, and it's quite interesting to note that, in fact, it's strongly centered on applications, on companies, on getting money from private companies, and so on. My talk will be mostly on basic research. I would just like to insist on one thing. In your country, too, you'll need basic research to develop original new approaches in applications. Without basic research, you have no applications, no original ones. You can only borrow from what has been done elsewhere. So my lecture, my talk, will be on steps towards life, chemistry. What has chemistry to do with this? With the emergence of living organisms. Let's start very early in the history, which is the history of our universe. Our universe started with a Big Bang. And this then was a universe which was very hot, which had no molecules, no atoms, particles. It cooled down, and then it formed atoms, it formed particles and atoms. This is the age of physics. There is no chemistry then. When it was cold enough for the particles to form atoms and atoms to link together to form molecules, then the age of chemistry started about here, 300,000 years after the Big Bang. The age of chemistry. Chemistry became more and more complicated. That means more and more complex molecules formed in the universe. They attached to one another. They defined compartments. And out of these compartments, at some stage, appeared a property which we call life. And life started here on our Earth. That's the age of biology. But it didn't stop at that point. Evolution continued, and thinking, a new property appeared, which is called thinking. This is represented here by this statue, this sculpture you may see here, by a famous French sculptor. And this person is supposed to represent the thinker. Thinking is the property of mankind. And that is steps towards life and towards thinking. So the question then is, how did it develop? What happened? How did this arise? We can look as a function of time that matter was first divided and then it became condensed. After that, it became organized. It became living matter, thinking matter, and maybe there is something else which is even more complex than our own thinking matter. That this was a progressive increase in complexity and in information in the matter which is making us. And it is the way towards complex matter, more and more complex forms of matter. At that stage, we should ask a very basic, very big question. What is this big question? This big question is, how does matter become complex? How can one go from an elementary particle to a thinking organism? Very long way in the evolution of the universe. Maybe there are even higher forms of complex matter. To give an answer to this question, mankind has invented an approach which we call science. Science is that area which will allow us to understand. And let's look at just three pillars of science, at three sectors, fields of science. On the left-hand side, you see physics. Physics deals with the laws of the universe, the laws on which everything depends. And on the other hand, biology deals with the rules of life, the way living organisms function. And what is chemistry doing? Chemistry tries to build a bridge between physics, the general laws, and biology, the organisms living on our planet Earth, and which then are an expression of these laws. How can one bridge general laws of the universe to the emergence of specific living and thinking organisms, like on our planet? Remember that from the slide I showed at the beginning on the Big Bang and so on, and the evolution of the universe, we are just one spot in space and in time. We as human beings are on a planet which is one place in our huge universe, and there's probably life and thinking in other places. There's very certainly life in other places in our universe. Now, the answer to this question of how did it become complex is what I would call self-organization. I mean by that the appearance of complex matter, which led to life, living organisms, and thought, thinking organisms like human beings, happened spontaneously, but on the basis of the laws of our universe. In other words, self-organization is a process by which the universe gets organized in some ways, and this organization has then led to the evolution of thinking organisms. One may say that the laws of our universe, that the structure of a universe is such that it will organize. It is not an accident. One can even claim that it is a cosmic imperative, that our universe is built in such a way that it will generate life and thinking, thought, in some regions of the universe. Now, self-organization, which is, for me at least, the basic force driving our universe to more and more complex forms of matter, at present we consider it two ways, because there is not yet a complete unitary theory. But on one hand, there is the large scale, the structure on the large scale, the structure of our universe, the cosmic structure. And this results from the action of gravitational forces operating on inhomogeneities in the density of matter and expansion at very early times after the Big Bang. That is not what we are part of. We are part of visible matter, of complex matter, which is molecular matter, which forms through the action of electromagnetic forces acting on the building blocks of matter, of visible matter, of atoms, of molecules, through sort of random structural combinations, which progressively lead to organized matter, then to living matter, and then to thinking matter. So chemistry, among these sciences, the different fields of science, chemistry deals with the structure of matter and the transformation of non-living and living matter. Chemistry covers both the non-living matter and, of course, the living matter, because all organisms are built on molecules. Now, mankind and scientists had been, over the years, had found out that matter is made of elements, of particles, of units which define the basic bricks of matter. And this was progressively developed, led to a set of elements, of bricks of matter. And it was in the 19th century, around the middle of the 19th century, that was beginning to understand that these elements which had been discovered could be classified one could put order in these elements. They were not just chaotic. One can put order. And the most relevant, the best known person, the one who contributed most to this recognition of the organization of the elements of matter, the bricks of matter, was a Russian chemist, Dmitry Mendeleev, who in 1869 published a very famous, most important paper, which you see here in a German journal, chemical journal. And what it means is, I translate it into English, on the relationship between properties and atomic weights of the elements. Mendeleev had recognized that if one looks at the atomic weights of the elements and their properties, one could put them in a table, one could organize them in columns and in rows. And here you see the first publication which has been dealing with this organization of the bricks of matter. This is the most important paper in the history of science. I would like to insist on that. This paper is one of the most important papers in science ever written. You notice that last year it was the 150th anniversary of the publication of Mendeleev. He went even further. You see that these elements are organized here, but he had also some question marks here and here. You may see that. These question marks mean that he was considering that there were empties, there were holes in the table, and these were elements which would be discovered later, and they were discovered. So the table was not only organizational, but it was also predictive, which is a very important feature. So this is now called the periodic table of the elements because the periods, the elements are classified into columns and rows. And nowadays, that's the way it looks. All chemists, all scientists, I would say, or even all people should at least have seen that. Why do I insist on that? Because these are the bricks of visible matter. These are the bricks which make us. These are the bricks which make visible matter in our universe. I would like to insist on the importance of this. This table shows you the bricks of visible matter, and there are no other ones. This is incredible, but it is true. And if there are, here you see H, hydrogen, He, helium, lithium, and for instance, kitchen salt contains sodium, Na here, and chloride here on the other side. These elements make up our visible matter. If there are living organisms somewhere else in our universe, they will be made of the same bricks. They will have similar molecules, and the rules for building up molecules from these bricks will be the same. So if you think about it, it means that mankind has been able to discover what visible matter is made of everywhere in our universe. And any living, any thinking organism anywhere else will be built with the same elements, the same bricks. And this is the playground of chemistry. That is what chemists play with. They use these bricks and they build these bricks which define atoms, and they build houses with them, which are molecules. So out of the putting together, linking together these different bricks, you can generate molecules, which are as I said, the houses resulting from the combination of these bricks. Now, the atoms then lead to the molecules by linking atoms together. And this is the development of molecular chemistry, which results from binding these atoms together by strong linkages, which are called covalent bonds, and generating complex molecules. Let's look at two milestones of that. Two milestones in molecular chemistry. The first one I would like to mention is in 1828, a German chemist, Friedrich Wöhler, made urea, this small molecule here, from another entity, which is called ammonium cyanate. Urea is contained in living organisms, it's contained in urine in living organisms. Ammonium cyanate is not a part of the living organisms. So by doing that in the laboratory, Wöhler showed that there is no difference in essence between molecules of non-living matter and molecules of living matter. This was very important because it showed that life is built on similar bricks that the non-living matter. About 150 years later, this very complicated molecule was built up in the laboratory by the combined efforts of two groups of chemists, one in the USA, led at Harvard University by Robert Burns Woodward, the other one at the Polytechnical School in Zurich in Switzerland, that group being led by Albert Eschenmoser. This molecule is much more complex than urea, so it shows how much progress chemistry has been making in the art and science of building complex molecules. Of course, these people were helped by a whole range of collaborators who contributed to put the right atoms in the right position to generate this vitamin B12, which we have in our body. It took many, many years. It took 12 years, almost 10 to 12 years in the laboratory, but this was the common efforts of many collaborators. So altogether, one could say it took probably 100 years of man and woman years. So that was a high point in the production of very complete molecules in the laboratory. But since the 50 years, since 1970s, of course, molecular chemistry has developed, has become more complex, new things have been made, and of course, it will continue to evolve. New chemical reactions have been discovered, new compounds have been made, new materials, new molecules, new drugs, and it will continue. So molecular chemistry is an adult, strong, powerful science to build very, very complicated molecules, which are also parts of our body. We are made out of such molecules. But then we can ask a question. Is there something else we should think about? This is the molecular world. What else should we think about? Let me introduce that, but by some examples in biology. Here you see the blue sphere, which is a cancer cell. And you see two violetly purple-colored bodies, which are killer cells. We have killer cells in our body. These killer cells have a mission. They have a task. They must find out which normal cells have become abnormal, have become modified, and have become cancer cells. And when the killer cells find a cancer cell, they have to destroy it. So the question is very important. How do killer cells recognize that the other one is a cancer cell? They need to recognize it so as not to make a mistake. Otherwise, they might destroy a healthy cell. So something tells the killer cells that the other one is a cancer cell and not a healthy cell. Similarly, this is a white blood cell colored in rose artificially, and here the blue dots are the HIV virus particles. When these particles get in collision with a white blood cell, they can infect the white blood cell. That means that something tells, if I may say so, the virus that it has reached the goal and now can infect. So something must happen between the cancer cell and the killer cells, the white blood cell and the virus, which makes them know what is happening, what is going on. And this is due to molecules. All these bodies are made of molecules that are defined by a membrane. This membrane contains specific molecules, and it's by the touching between the entities here that this information is used and gives information to these bodies that what is occurring, what's happening. So that means that molecules, of course, are the basic stone, but something must happen between molecules, between cells, so that they know what is going on. And this is the field we have developed now 50 years ago, starting, which is we have called supramolecular chemistry. This name, when I meant by that it's a chemistry beyond the molecule, which has to do not with isolated molecules, but with molecules getting together, interacting with one another, touching each other, and therefore being able to get together, to interact, and to perform molecular recognition. This is a very important the property of how do molecules recognize one another. This is the basis of the recognition also in biological systems like between cells. Other functions which have been studied in this field are the reactivity between molecules and the transport of molecules through a membrane of a cell, for instance. How is this transport regulated? How do cell membranes regulate what is going in and out of the cell? So molecular recognition is the basic process on which all depends. Life depends on molecular recognition. Without molecular recognition, we would not exist. In our body, molecules all the time recognize each other and then perform functions. Let's have a better look at molecular recognition. Molecular recognition first requires interactions. They have to bind together to interact. This is, of course, normal. Otherwise, they would ignore each other. But that's not enough. You need also information. Without information, there is no recognition. You know that very well. You cannot recognize somebody in the street if you don't have information about that person. So molecules are the same. Molecules recognize each other on the basis of what information they contain. And the way to represent that is first to consider there is a complementarity in geometry and interactions between molecules, which leads to recognition. And the very simple, very clear image has already been proposed at the end of the 19th century by a German chemist, Emil Fischer, when he said that molecules fit together like Schloss und Schlüssel, like a lock and a key, as represented on the left here. It is this fitting together of molecules, which is sort of the basic principle of molecular recognition. Of course, we know that it's a bit rigid. It's more complicated, but the basic image is really correct. I would also like to insist on the fact that he got his doctorate in Strasbourg, in my university here, in 1874. This was, of course, we are very proud of that. Now, the most important information system for us human beings is the one which makes us, the one which defines a human being and which makes a human being different from an elephant or a tomato different from a dog. And this is contained in the genetic information, which is stored in the famous DNA double helix you see here on the right. What is the basic features? What are the features of this double helix? What is this storage of information in the genome of living organisms? It's a very simple program. It is a long chain of chemical entities seen here. And on this chain are sticking 4 different chemical groups. These are rather simple chemical groups here. For a chemist, that's a very simple molecule compared, for instance, to vitamin B12, which we saw earlier. And there are just 4 of those letters, which have been given the names adenine A, guanine G, thymine T, cytosine C. So, the genome of our living organisms on our planet. On other planets, it can be different. But on our planet, living organisms are defined by their genome, and the genome is written with a sequence of these letters, a very long sequence of these letters. And two such chains then wrap around each other to form this famous double helix. So the genome program which makes living organisms on our planet is just written with a sequence of these four letters. How can you read this letter, this genome? You have to read it. It's not enough to store information. This happens in a very simple way by pairing up, making pairs of these letters. The letter adenine forms two interactions represented by these small dots here in the green square here, the green represented by this screen here, where these little dots represent the interaction, two interactions between adenine and thymine. You will see this is a slight variation. Another one is between guanine and cytosine, and there are 3 points of interaction, 1, 2, 3. So this is a binary system, like what is going on in a computer, where the system is 0, 1, 0, 1. Here it is 2, 3, 2, 3, 2 points of interaction or 3 points of interaction. And that is enough. Molecular recognition is processed by these interaction patterns between pairing up between 2 letters here by 2 pairings and 3 letters by 3 points of interaction. In other words, evolution on our planet led to a system where the information for living organisms is stored in a sequence of 4 letters and 2 ways of pairing them up. Why is it like that? That's an interesting question. Probably because it's enough. If you have 4 letters and 2 ways of pairing, you can write the message and you can read it. So chemistry, you have realized now, is also an information science. The storage of information is at the molecular level, and the processing of the information is at the supramolecular level, the level of interactions between molecules, the level of populations of molecules getting together and interacting with one another. So one can claim that chemistry is, of course, the science of the structure of matter, of the transformation of matter, as I have already said, but very importantly also, it's the science of informed matter. Molecular matter contains information, and it's the contact between molecules which is a way to process this information. So if we go back to Emil Fischer's locks and keys, suppose we have here a lock and these 3 keys. Of course, the red key fits. So this question of understanding molecular recognition led to many, many studies in many laboratories around the world, and molecular recognition processes were progressively understood and led to many developments. One major development is, of course, to understand molecular recognition in living organisms, in ourselves, in our body. Now, this is basic science. This is basic science, and many laboratories, as I said, have studied that. This is basic science on which applications depend. I have listened a little bit to the talks which were before my talks. I understand they were very practical. They were very much directed to developing companies, to getting in touch with the private world. That is fine, but you need basic research. Otherwise, you cannot develop any application. And if you do not develop in your country basic research, you will not have original applications. I would like to insist on that. It's not a question of setting up companies only. That is important. But if you want to have new companies, new applications, you need to have strong basic research. Let's then look at applications which came out of the supramolecular chemistry. Most importantly, molecular recognition is absolutely crucial for drug discovery. Why? Because a drug is a molecule which is designed to interact specifically with a given biological target. And this interaction is a recognition interaction. In other words, a molecular drug is a key for a biological lock. It has to selectively bind to the right lock and not to make a mistake. This is drug discovery, which is based on molecular recognition. We also developed some other things. I just mentioned a few of them. We developed some other substances which can be used in medical diagnostics. For instance, that's the unit which can have a red luminescence, a red color. It shows a red emission, it shines red light, so to say, and it has been used to develop a medical diagnostics apparatus, which is shown here, and which is used in many hospitals now. It's used by connecting this red bulb, so to say, this nano bulb, this nano lamp, to immunoproteins for medical diagnostics. Another property which we have developed, and we are not the only ones, of course, many people work in the field, is gene transfer. Gene transfer consists by artificial synthetic vectors, consists in making molecules represented by this red ellipse here to bind the gene, a piece of DNA, and to help it cross the cell membrane to generate and to ultimately generate the protein which is defined by this DNA. This is a very important process because in doing so, you can make a cell secrete a protein which may be of interest for biotechnology or which may be a protein of interest as a possible biological drug. Furthermore, this process also is very important for biotechnology. By doing so, you can generate what are called genetically modified organisms. Now, let me say two things. First of all, these genetic modifications, which can be performed by using synthetic vectors for genes to introduce them into cells, can be very important for gene therapy, for correcting genes which have been transformed, which are not the correct ones anymore in a living organism, for instance, in the lungs. On the other hand, the same process used in biotechnology, as I mentioned, leads to genetically modified organisms. I would like to insist on the fact that nowadays, people are afraid of genetically modified organisms. This should not be the case. Genetically modified organisms can be controlled. We know what to do with it, and we need them. I would like to express this very strongly. Don't believe in all these people who say this is dangerous. It is not dangerous. We can control it. Of course, you can already make it dangerous, like my hands can be dangerous too. But it can be controlled, it is controlled, and they are necessary for the development of mankind. Then there is also the question of materials. We have also developed supramolecular materials on the basis of supramolecular chemistry. And I would just like to illustrate one application which resulted from that, which was for us really very satisfactory. We had made polymers, polymeric entities, that means what we might call plastics of supramolecular type, which were made as biocompatible polymers by a small company called Xeltis. We had published the first paper that was basic research in 1990. A small company, Xeltis, I mentioned, had developed these biocompatible polymers, and in 2013, that means 23 years after the basic research, and of course this basic research was then developed by many laboratories around the world, this company made a biocompatible supramolecular polymer for cardiovascular implants to correct the heart of children who had a severe congenital malformation. This was done, and here is the first little girl, Dominica, who had been, this is 3 months after implantation in her heart of a wall of a piece of this biocompatible polymers and implanted in her heart by Leo Bokeria, a professor at the Bakulev Scientific Center for Cardiovascular Surgery in Moscow. He's a famous cardiovascular surgeon for pediatrics, that means for children, and here she is. She's fine, and he's happy, of course, also. And we were extremely happy that the compounds which were initiated in 1990 led to an application like children being fitted with this new polymers. Now, many children have been now fitted. I put here 10, but there are many more now. And the same company has also then developed heart valves in Budapest, which have been then put to use in clinic in Budapest, in Krakow, and Kuala Lumpur. In more than, these were 12 children. I suppose now there are more. So this was just as an illustration that basic research leads to original important applications, but it may take a long time. You should not hurry up. Of course, some things have to go faster, but the transformation of basic research into applications, especially in the field of human medicine, is a long way. It takes time. You cannot get it over the weekend. Now, let's go back to the theme which I had started earlier, which has to do with this question of organization, self-organization. Supramolecular chemistry led to a better understanding of recognition between molecules. And this then led to trying to build up in the laboratory systems which can self-organize, directed by molecular recognition. It means the goal was to set up chemical systems which would spontaneously generate supramolecular architectures, complex shapes, complex entities, but in a controlled way, controlled by the information contained in the building blocks. And let me just illustrate that, but by one example, just one slide later on. But first, I would like to insist on one thing, that living matter is, of course, self-organized matter. And one of the simplest expression of that is a virus. Like you know that right now we are in this pandemic of COVID-19, SARS virus. Virus is a bunch of molecules. A virus is not living. A virus is dead. It only gets living when it encounters a living cell. So the virus I would like to illustrate is the tobacco mosaic virus. This virus is a sort of a building. It's a big building on the molecular scale, made from 2,130 protein bricks, subunits, which get together, recognize each other by attaching by surface-to-surface recognition. These pieces, this is another representation, that's a better, larger one. And this surface-to-surface recognition leads to the connection of these things by supramolecular interactions. And then, as you see on the left, they can get together and generate this sort of column with a hole in the middle, which contains the genome of the virus. So this happens spontaneously, but in a very controlled fashion by the information contained at the surface of these molecules. And this is a sort of a programmed chemical system. It runs like a computer. You input information, it runs, and it gives as an output the virus. So these programmed chemical systems, the program is molecular, information is stored in the components, and this operation, the processing, is supramolecular. It occurs by a recognition, what you may call a recognition algorithm, defined by the way these entities interact. Let me just give one example of these things which have been done in a laboratory, in many laboratories around the world. We will consider the bricks to be organic molecules which are able to bind metal ions like iron or copper or other metal ions. And these metal ions, metal cations, are the cementing units, the connectors which bring these molecules together. So, given the variety of such self-organized architectures, which we call metallo-supramolecular, because they are made of molecules and metal ions. For instance, we have made double helix here on the left, and the triple helix you see here. These have nothing to do with DNA. They are totally different. They have a different structure. They have different entities which make them. We wanted just to show that you can make spontaneously double helices and triple helices on the basis of this self-organization of non-living matter. That's another one. That's what we call a grid, where molecules are horizontally and vertically positioned by binding here metal cations. This is copper, not in this case it's silver. It's copper, another one we have made. So this is a grid with 9 silvers holding together 6 molecules in perpendicular way. Here you see what we call a nanocylinder, where you have 3 linear molecules in reddish rosy, 4 planar flat ones in blue, and they are linked together by 12 spheres, which are here copper ions. So you can see there are 19 components, and when you mix together these molecules, the red ones, the blue ones, and the connectors, they assemble to generate this nanocylinder in a very specific fashion. These are just some other illustrations to show you that many more have been made, and many, many, many more than what I show you here have been made. And this is a very, very important field now in chemistry, using metal ions to organize molecular matter. It can also be, for those who are interested in applications, of course, as I heard earlier, it can be a major contribution to nanoscience and nanotechnology because, as you know, nowadays, presently, we use nanofabrication techniques, nanomanipulation techniques to make these fantastically powerful devices, which we call computers, or let's say cell phones, and so on. Sure, but that is something you have to make, you have to fabricate. If we can define, if we can discover, if we can develop systems where these devices are generated spontaneously from their building blocks, that means a spontaneous but a controlled generation of these large architectures by spontaneous self-organization of the building blocks, then we will have reached the possibility to go from fabrication to self-fabrication, which is, of course, the ultimate fabrication. That is what one would like to do, to just have the pieces, to put them together, and let them spontaneously generate the final device. There is progress being made towards that, and in the future, we will see certainly much more. Now, let me just finish by showing you where we are going now, and after that, I will give some general comments, and more, let's say, general conceptual comments. What I have shown you up to now, I've insisted on design, storing information in the building blocks, programming the system so as to be able to lead to the controlled generation of functional, molecular, and supramolecular entities. But then there's another approach, which is to do that a step further in complexity, and the next step in complexity, to develop systems which can select what they need to build themselves up. For this type of selection process to occur, you need the diversity of building blocks because the system needs to select the good ones, so to say. And also, you need dynamics. That means when two such molecules collide with each other, this may be the right collision or not the right pair. So there has to be a possibility to separate again and to reform, to reassociate. This then leads to the idea that where this type of chemistry leads to the concept of a constitutional dynamic chemistry. It means, and I will only give you the ideas here, it means that the chemical objects which are concerned by this field here are dynamic in their constitution. It means they can fall apart, they can dissociate and reassociate. And this reassociation between the pieces can be the same as the starting one or can be different depending on the conditions. If the conditions change, this object may change also in its constitution. In other words, it may adapt to processes, to agents in the environment, and this leads to adaptive chemistry. Adaptive chemistry is a chemistry which we are now mostly working on, which consists in studying systems where the building blocks can separate and recombine, and in doing so, they can also respond to solicitations, to effects, to agents in the medium. So the chemical object will adapt to the environment, to the changes, to the agents, to whatever happens. And this has been used, I show you just a slide where I indicate for what it is good. The adaptation occurs through variation in constitution at both molecular and supramolecular levels, and it has been used to develop biologically active substances, to search for them, to make dynamic nanostructures and dynamic materials. This is rather interesting. I have no time to go into that because of time limitations, but you can make self-healing materials, responsive materials, adaptive materials, and technologies. For instance, self-healing polymers are polymers which you can cleave, and then they will spontaneously repair, which of course is a very interesting property. So I summarize the pathway which we have followed, and then, as I said, I will go to some general considerations. We start with molecular chemistry, which is the building block. Of course, the atoms are the building blocks of molecules. And then we start with molecules which can get together and lead to supramolecular type of systems where molecules interact with one another. They interact together. They get organized on the principles of molecular recognition, the way molecules interact. Then dynamic, we want them dynamic so as to be able to adjust and to respond and to adapt. And these are the present steps towards complex matter. The next step is also developing, where one tries to have also systems which are closer even to living systems and which will be able to operate in conditions where living systems operate. Let me then give you some general remarks, general comments. I suppose you have noticed that chemistry can do things which don't exist yet. So the essence of chemistry is not only to discover what already exists, but also to create novel expressions of complex matter. The book of chemistry must be written, not just to be read. Of course, in nature, around us, in our body, we ourselves we exist. We are made of molecules. We have to understand them. We have to read what they are. But we can also write new ones which do not yet exist. And also the score of chemistry has to be composed, not just to play. The score will lead to music, but you have to compose it and not only to play it. So chemistry has creative power, which may be represented again by another sculpture of this French artist, Auguste Rodin. Rodin, you would say, in French is Rodin. And this is the hand of the artist expressing out of a stone a sculpture which is not contained in the stone. The stone doesn't know what this sculpture is. It's the hand of the artist which does it. In the same way, chemistry, out of the elements of matter, expresses entities which do not yet exist. And this is then one can call chemistry the art of matter. It's the artistic way of shaping matter from its elements, from its bricks. This was already since many years ago by a very, very famous artist. You certainly know Leonardo da Vinci. He is the person who is best known for painting Mona Lisa, the Gioconda, the famous painting which is in the Louvre Museum in Paris. probably the most famous painting in the world. So he was an artist, of course, a painter, but he was also a scientist, and he was an engineer, an inventor. So he wrote a very interesting and very strong sentence many years ago. You see, he died in 1519. Last year was also the 500th anniversary of his death. He wrote, "Where nature finishes to produce its own species, man begins." So this is its own species. We are part of that. These are the natural, the ones, the things, the entities in nature on our planet, and of course on other planets too. Man begins using natural things. What is this? These are the bricks of the periodic table of the elements, the bricks which make up visible matter in our universe, in harmony with its very nature. This means in harmony with the laws of the universe, the laws of nature. And everything, of course, the build-up of all these different objects which we can make from the bricks, this build-up follows the basic laws which allow them to do it in a given way and not in others. And then the ending of this sentence is a very strong one, to create an infinity of species. In other words, Leonardo da Vinci here says that by using this capacity of recombining things, using natural things, of course, in agreement with what is allowed by the basic laws of physics, we can generate an infinity of different entities. Let me just show, maybe he thought about it in the following way. A painter has colors, and he has brushes and can make paintings. The colors, this is physics. The painting, this is chemistry. The painting is a new painting, and all the paintings are different. They all depend on colors, but they are not the same paintings. So there's an infinity of paintings you can make with the colors. Like there's an infinity of pieces of music you can write with sounds. The sounds are the acoustics, are the laws of acoustics. Chemistry are the pieces of music, the symphonies you write with these sounds. Let me just indicate that if you go back in the history, you come to the Greek mythology, where a Titan, Prometheus, stole the fire of knowledge from the gods and gave it to mankind. This is the mythology at that time. And here you see having the fire of knowledge and running away and hoping that the other ones will not catch him. But they didn't, and so he gave this fire of knowledge to mankind, and here he shows it clearly. He holds it out. But we must realize that we cannot give it back. What we know, we know. What we know, we cannot erase. What we know, we cannot give it back. We have to learn to live with the knowledge which we gain, which means that our path as human beings, and the same path is certainly followed by other living, thinking beings in other planets around our huge universe. Our path leads us from the quest of knowledge. First, you have to look for basic knowledge, as I already insisted. And this will allow us to control our destiny. We already are able to do this. We already are able to modify ourselves by different means, for instance, by implanting different teeth, by implanting another heart, or different other things, and we will be able to control our destiny. The destiny will not be anymore, at least if we want it, but I think I'm convinced we will do it, will not in the hands of what we call nature, but it will be in our own hands, which in some ways is also in the hands of nature because we are a product of the evolution of our universe. So let me finish with a mathematician. I haven't said much about mathematics. This is a very famous mathematician, David Hilbert, who is buried in Göttingen in Germany. And this is his tombstone in the cemetery in Göttingen. Here you see it. This is his tombstone. And on this tombstone, I've written 2 sentences, you see here, 2 sentences. These sentences, I want to show them to you. The top sentence is, wir müssen wissen. We must know. This is already a very strong statement, very strong statement. But it's a statement we scientists have in ourselves. We want to know, we must know. But the next sentence is even much stronger. The next sentence is a vote of confidence. Wir werden wissen, we will know. So the first sentence is a statement we must know. The second is a vote of confidence, is the conviction that we will know. And that is thanks to science. We will know thanks to science. We must talk science to people in the streets. I give often public lectures, similar to what I'm giving right now, to make people think about science. And we can add to this that don't forget, be convinced that science shapes the future of humanity. So I encourage all of you to participate. And all the students who are listening to me here, please participate. All the people who are listening, try to learn some science, because science shapes your future, science shapes your destiny, and please participate. So to conclude, I would like to thank the persons who have organized this meeting for inviting me to it, to be able to share some of these general ideas on how chemistry has developed, on the central role it is playing. And I hope that you will then look at it in a given way and see what is the power we can get from it and how we can use it, and how it will also definitely be present in our future and shape our future. Thank you very much to all of you.
Hi, dear ladies and gentlemen. I was glad to hear the talk about the professor of Jan. It was very interesting. Меня выключили. Мне камера выключена. Меня выключено.
It's all right. Take your time. Take your time.
Да. Профессор Изтлeuов, вы можете начать говорить? Мы вас видим.
Они вас видят.
Good evening, dear colleagues.
Hello.
Do you hear me?
Yes, I hear you very well.
It was a very interesting talk about the supramolecular of chemistry. It was very interesting. I was glad to see you. I was glad to hear your reports about this chemistry. It was very interesting, and I understand the nature is a very unequal system. There's created a very unequal molecules, and I hope that it's very help at the future for the finding the many medical preparates for the fight with the many types of illness and other types. And I have one question for you, Professor Jan.
Yes.
How do you think? By our theory in the Soviet Union, we have talked that the living matter, is created on the land. And how do you think the living matter is created on the land or on the water?
Yeah, this for the moment we don't know exactly how this happened. It's possible that, of course, it was, it's difficult to know. Many people are now working in this area, which is called prebiotic chemistry, chemistry before life. to understand how molecules have become more and more complex as time goes, and then at some stage have had this property of being able to reproduce itself, to have a metabolism, to reproduce, to carry information to the next generation. Many people are working on that. We, for the moment, do not understand for the moment how it happened. There are many theories. There were theories also put up by Russian scientists. There are theories put up by all over the world, by many people around the world. Nobody knows for the moment what is the exact pathway, but there's progress being made. And I think in the future we will know about it. It takes time. It's a complicated process. So I cannot tell you whether it will happen in water or on the earth. Probably it happened in both places. It happened, what was on water, at some stage it was on the earth. And so it was organized. It had these forces which bring molecules together. We don't know really yet, but it's a process which will be discovered.
Yes. Thank you. Thank you.
Can you put full screen, perhaps, please? I think it's not possible, huh? Because I see you, but I see you only very small. So if you have other questions, I am open to questions. You think you can do it?
The next talk, the next talk will be the beginning of Yessimov Begen Omarovich, the professor of South-Kazakhstan State University by the M.Auezov. They have talked about research in chemistry, which we will have to spend at our university. Please talk about it. Begen Omarovich.
Oh, thank you. Good evening.
Yes, for me it's afternoon. For you it's evening.
Allow me to start my speech about the place and role of silicon and the silica in the life of our planet. As can be seen from table first, after oxygen is the second most popular chemical element in the Earth's crust. The upper part of the Earth's crust is the habitat of humanity. Oxygen, silicon 25 and 7%. According to scientists, silicon has the same role in the Earth's crust as carbon in the animal and plant world. In the geochemistry of silicon comprises its extremely strong bond with oxygen. In the upper part of the continental crust, the content of silica is 16.8%. So, siliceous and own silica minerals in the Earth's crust are contained more than 18.7%. Silica minerals have been known to man since the Stone Age. Then the use of silica stone tools, more often of chalcedony and quartz, lasted for several thousand years. Later, around 3000 BC, the production of glass, also based on the silica, began. Thus, before other minerals, the man knew and found application the silica. Nowadays, the importance of spheres and the fields of application of silica had to rate. These are quartz, glass, ceramics, optical rock, crystal quartz, electromagnetic quartz, piezo optics quartz in radio engineering, quartz lamps, chemical glassware, jewelry, technical silica for solar batteries, and many other priority materials. The exceptional role played by silica in biochemistry and in the human life is quite clear. Next, I would like to pay your attention to two not enough studied properties of silica as a raw material in the ceramic industry, obtained in the during of your experimental research. According to modern concepts, the silicon oxygen tetrahedron is the minimum structural unit of all silicates. In them, each silicon is always surrounded by 4 oxygen located in the corners a tetrahedron. Thus, were established the place and the role of silica in the formation of huge masses of igneous rocks in the crust, the primary sources of the minerals of the silicate growth. During the weathering process of any rocks in them, quartz is a chemically resistant mineral and therefore accumulates in the places, sandstones and others. At one time, one characteristic feature was noted in the chemistry of silicon. Silicon, unlike aluminum, iron, titanium, and others, does not form chemical compounds with organic soil acids. If these elements from readily soluble complex salts and carried away with aqueous, then quartz and other forms of silica from decomposed clay minerals remain in place. In our opinion, this scheme underlies the formation of micro-silica deposits, sometimes with a thickness of up to 100 meters or more. Most often, micro-silica or dusty quartz is a residual product of weathering of siliceous limestones, quartz, dust, or other siliceous rocks. Natural microsilica is often monomineral that futures set natural microsilica with a content of 96% is used for the production of casting paint. The structure of natural microsilica is unique. It is shown in figure first by the example of the samples being studied from one of the deposits of the Turkestan region. We observed a similar structure. Microsilica wastes of the latest production of technical silicon in our country, operating on quartzite mineral raw materials, should say that the daily mass of this waste is 16 tons. The content of silica in them is also very high because in the production of technical silicon, quartz raw minerals must contain silica 19 and 7%. The waste from the production of technical silicon are products associated with waste gases and dust, and are called by the manufacturers microsilica. This microsilica is an ultra-fine material consisting of particles of spherical shape. Then the main component of the material is amorphic silica. Together, Professor Vereshchagin from the National Research Polytechnic University, Russia, we carried out experimental research on the synthesis of modern types of technical and building ceramics using both natural and industrial silica. We have found a very effective influence of both types of materials on the course of physical-chemical processes of formation of phase. Formations during the heat treatment of ceramic masses. We have also studied the change in the behavior of mulite, the main mineral of silicate ceramics, due to the dispersion and the intensifying chemical activity of microsilica in our compositions. A quantity of mulite neoformations increased. Thus, one of the priority types of technical ceramics was obtained at a temperature 15-17 degrees lower than the traditional one. And the samples of new building ceramics were synthesized with a 7 greater effect in terms of heat treatment and water absorption indicators. The developed compositions and the technology made it possible to carry out the most optimal energy-saving synthesis of mulite, which is responsible for a low coefficient of thermal expansion, tension, and bending strength, the aesthetic appearance of ceramics. In industry, this will give great energy benefits. Natural silica, for the formation of which nature has spent millions of years, and artificial silica obtained by difficult melting in a or thermal furnace at temperature of 1,800 to 500 degree are very identical. In our opinion, in composition, structure, and properties belong to a unique and valuable raw materials. This type of raw material should only be used to obtain new and priority materials with the highest added value and high demand. Everyone remembers the words of the great Dmitry Mendeleev. To heat the stove with oil is the same thing as with paper money. Mendeleev was right. Much in everyday life and the technology is made on the basis of oil. In our opinion, the same beautiful fate awaits the micro-silica. Using it in elementary and ship production does not really matter. We know 21st century has been declared the century of ceramics. Ceramics, affordable, reliable, durable, aesthetic, eco-material. Thank you for attention.
Thank you for your reports, Professor Begen Umarovich. It was very interesting to hear you, and it was today actual to recycling the waste in our republic, in the world, because the ecological problem is the most important in our life. And I hope that at the future, our country and in the world to make more green technology and waste industry in the world. And today we have very interesting talk with Professor Jan and with Professor Begen Umarovich. It was very interesting. I hope that our collaboration is not enough, and I would like to invite Professor Jan to our university, South-Kazakhstan M.Auezov University, to the International Scientific Conference, Industrial and Technology in the November. It will be in our university in South Kazakhstan, and I hope you to your health, and I hope that we are meeting at our university. Thank you very much, and that's enough.